So parametric equations are equations with something called a parameter. And that parameter often is something called t for time, but also could be a parameter of theta. So parametric functions are used when we want to be able to say something like, we all know the projectile of a football, right, as we're passing it down the field, okay? Follows a parabolic type curve, right? But unfortunately, with an equation like y equals the quantity, or a times the quantity x minus h squared plus k squared, or plus k, it doesn't really tell us where that ball was at a specific time. It tells us the height of the ball, right, at any given time, but it doesn't tell us where it was at a specific time. And so that's where it's useful to have something called a parametric equation. With a parametric equation, you end up with two equations, one with x, one with y. Both of them have a t, or some other parameter. So for example, if this were a football or a baseball being thrown, a rocket, okay, it's going to have a parabolic curve to it, like a parabola. But what's going to happen is it's going to, if you use a parametric equation, you can actually figure out where it is at time t, at for any time t. Okay? So in this case, we have a rectangular equation, y equals negative x squared over 72 plus x. Okay, that would be our normal equation. Parametric equations talk about it in terms of both x and y. Okay, and involve a t. So what this is called is a plane curve. Okay, and we're going to look at these in just a second. So don't worry so much about writing this out. Just understand that it's going to have equations with both x and y. Okay, and we're going to use our t as our parameter. Okay, so far so good? All right, so let's look at an example. We want to be able to sketch a plane curve, and we're told that x is equal to t squared minus 4, and y is equal to t divided by 2. And this curve is defined when t is between negative 2 and 3. Okay, which doesn't make a lot of sense, as we don't usually think about time as being in a negative time. All you do is you make a table of values, and then you plot it using only the x and y. And then we denote our direction. So table of x and y values. When t is negative 2, we plug negative 2 in for t in our first equation that involves x. So we're taking a negative 2 and squaring it, and we're subtracting 4. What's negative 2 squared minus 4? 0. When we plug negative 1 into our x equation, we're going to have negative 1 squared minus 4, which is negative 3. We plug 0 in. 0 squared minus 4 is and then when we plug 1 in, 1 squared minus 4 is negative 3. 2 squared minus 4. And then 3 squared minus 4. Okay, those were all of the whole numbers between negative 2 and 3. That was our domain. Okay, now we're going to plug in those same values in our second equation involving y. So we'll take a negative 2 divided by 2 and get negative 1. Then we'll take negative 1 divided by 2 and get, and then we'll take 0 divided by 2 and get and then 1 divided by 2, and 2 divided by 2. Thank you. And then finally 3 divided by 2. Nothing more than plugging numbers in, right? Plug and chug. Okay. Then the next step is going to be to plot the x's and y's. So we're ignoring the t's now. When x is 0, y is -1. When x is -3, y is -1/2. When x is -4, y is 0. When x is -3, y is 1/2. When x is 0, y is 1. And when x is 5, y is 1.5. So now we graph this, and with parametric equations, you have to show the direction in which they were moving. So you do that by connecting the dots and then showing an arrow to show which way that was moving. Okay? What does that look like? A parabola. Vertex at -4, 0, opening to the right. So is it x squared or y squared? Y squared, yep, because x squared would open up or down, right? And our a, our 4p, is going to be positive here because it's opening to the right. Make sense? Okay. Nothing more than a parabola in this case. Okay. What questions do you have on this slide? Parametric equations. We have a parameter. Okay. Let's do another one so you get some practice with this. This time we didn't specify what the domain is. Exactly. Yep, we're going to give you x equals, y equals, and you're going to plug in points for t. Yep, and that's all this is. And then we're going to actually combine the two equations to be able to eliminate a parameter, basically. Okay? Not a big stretch. Nothing very abstract or far away from what you've done in the past. Okay? Now, they didn't specify a domain here, so we're going to have to come up with our domain. Okay? So we want to figure out where these domains overlap and what's acceptable. Okay? So if t is going, x is going to be the square root of t, and we're graphing in the regular rectangular coordinate system, meaning the real number system, what is our restriction of our domain as far as x is concerned, the x equation? What values of t can we have? Zero and up, right? Okay. T has to be greater than or equal to 0. Okay. Do we have any restrictions on the domain of the second equation? Are we taking square roots or dividing by anything? Nope. So we're good with that one, all real numbers. So we're going to only pick numbers bigger than or equal to 0 when we're plugging in our values for t. Now let's be sensible and use some good strategies here when we pick our numbers. 0 makes sense, right? Because we can take the square root of 0 relatively easily. 1's a good number. We can take the square root of 1. Can we take the square root of 2 very easily in our heads? So what should we pick next? 4, and maybe 9, right? And then we might get too big that we can't use it all. Okay, so let's try these numbers then. What is the square root of 0? What's the square root of 1? What's the square root of 4? And what's the square root of 9? Right? Same values for t. Let's plug them into our y equation. 0 plus 2, 1 plus 2, 4 plus 2, and 9 plus 2. Okay, I might have gotten too big here. Okay, so now let's plug in some plug these guys, plot these guys on the coordinate plane. So when we were at 0 for x, we're at 2 for y. When we're at 1 for x, we're at 3 for y. When x is 2, y is 6. And I'm already off my graph, aren't I? So 3 and 9 isn't going to work out so well for me. Okay? Looks a bit like a parabola, doesn't it? Going to have some sort of curve to it because of the square root of t. So we connect the dots, and then we don't forget our arrows to indicate the direction in which it's going. Okay. This somewhere. Yeah, don't go too crazy with the arrows. A couple's good. Okay, just indicating the direction in which it's going. Okay. All right. So sometimes we want to eliminate that parameter of t or that parameter of theta. And we'll see one with theta in just a moment. It allows you to represent the parametric equation in its rectangular form or the coordinate form. So to do that, you solve for t in one equation, and then you substitute that into your other equation, and you simplify. And again, we want to think about which equation will be easier to solve for t in, and then use that. So we'll eliminate the parameter, t or theta, whichever one it happens to be, by first solving for it in one equation and then substituting in the other to eliminate that t or that theta or whatever parameter it happens to be. Okay? So let's look at this next example. Should look familiar. That same problem we had before. Very good. All right, here's our next example then. So now we want to eliminate our t from either equation, or solve for t and then eliminate it. So which one's going to be the easier one to solve for t in? First or second? The second. So if we're going to solve this one for t, we'll multiply both sides by 2, and t equals 2y. Now we take that 2y and we plug it in everywhere we see t in the other equation. So x will be equal to 2y squared minus 4. What's 2y squared? Or the 2y quantity squared. 4y squared. Okay. Because when we square the 2, we'll get 4, and when we square the y, we get y squared. Okay. Now we want to factor out that 4, right? Because we like to have y squared equals 4p times x plus something, right? So we'll factor our 4 out. And then 1/4 will be equal to, or 1/4 x will be equal to y squared minus 1. Okay. So that looks more like our standard form of a parabola. Now, this is not going to be a very good 4P, right? 4P will be 1/16. There's no way we can graph that focus or the directrix very easily. So we're going to not do that for this one. But we know that it's a parabola, right? Opening right, because our 1/4 is positive and our y is squared. What's our vertex? Yep, 0, 1, right? Okay. Actually, that -1 should be coming to the other side, right? We're used to seeing it y squared, aren't we? We're used to having our 4p on the right-hand side, okay? And that -1 is the other side, yep. So y squared equals 1/4 x minus 1 plus 1 when it goes to the other side, okay? So what was our vertex? Zero, 1. Should be 0. It should be -4, 0. What did we do wrong? We did this up here too. I think we started up here and down a wrong path. This is really, okay, let's go back here. All right, so if we had, let's take our x plus 4 over here equals y squared, and we're 4y squared, and we're used to having that y squared on the left-hand side. So 4y squared equals x plus 4. And then when we get that y squared by itself, we would take 1/4 of the right side. That looks better. Okay, so what's our vertex? -4, 0. 4p is 1/4, so 1/16 is going to be bad, so we're just going to put our point here. Okay? And then if you wanted to find two other points, when x was 0, what's y going to be? What's 1/4 times 4? 1. So if y squared equals 1, what would y be? Right? So when x is 0, we're up here at 1, we're down here at -1. Okay? And there's our parabola. Now, if you're not sure how these guys open, we already graphed this, so we know it's going like this, right? If you're not sure of the direction, then what you can do is you can plot a point in, okay? At 0, we were at 1, at, and see what direction you're moving. At -1, we're at what? At -2, we're at what? And that will help us determine which direction we're going. So you'd have to plug in 2 points. It's so tempting to want to go arrows both ways. We have no restriction on our domain, so we could keep going, but that's the way we go. Questions on this slide? All right, next one. Which is going to be the easier one to solve for t? The y. Because it doesn't have a square root. Okay, I like that thought process. but it also has a t in the numerator and a t in the denominator. We can go either way. Both of them have their merits. Which equation do you want to solve for t first? X or y? If we work with this first one, x times the square root of t plus 1 is equal to 1, right? So square root of t plus 1 is 1 over x. Square both sides. T plus 1 is 1 squared over x squared. And so t is equal to 1 over x squared minus 1. Okay? If you had worked the other way, you'd have to cross multiply. So y times t plus 1 is t. So yt plus y equals t. Get the t's to one side, factor it out, and away you go. So they both work. This one is not really advantageous to go one way or the other. Okay? So everybody okay with the t using this one? The x? Okay, so we're going to plug this into our t for y. And we'll have 1 over x squared minus 1. And then 1 over x squared minus 1 plus 1. All I've done is taken the 1 over x squared minus 1 and put it into t's spot for both. This should say minus 1 is a poor writing. Okay. So this is 1 over x squared minus 1 over minus 1 plus 1 just gives me 1 over x squared, right? Okay. Yep, flip and multiply, right? We're going to invert and multiply. So if I multiply the bottom by 1 over x squared, or x squared over 1, multiplying the top by x squared over 1. Okay, the bottoms are going to cancel. They're gone. So I have y equals x squared over x squared is going to be a 1, right? X squared times a negative 1. And we're done. And we're not going to take the time to graph that. Okay? We won't take the time today. Okay? But yes, they could ask you to graph it. Okay? All right, so one more example. Okay? X equals 3 cosine theta and y equals 4 sine theta. And we want to eliminate our parameter. All right, so no good way to eliminate theta, is there? Could divide by 3 and then take the inverse cosine, and it's going to be a mess, isn't it? Okay, but do we have any trig identities that involve both x and y, or I'm sorry, both sine and cosine? What's our trig identity that involves both sine and cosine? Tangent, be sine over cosine, but then we're still going to have a theta in there, aren't we? So we want to try to eliminate that in some manner. Do we have a Pythagorean identity that involves sine and cosine? Sine squared plus cosine squared equals 1, right? So if the cosine of theta is equal to x over 3, and the sine of theta equals y over 4, and sine squared plus cosine squared, or cosine squared plus sine squared equals 1, right? So x over 3 squared plus y over 4 squared would be equal to 1. We've eliminated theta. But what is x over 3 quantity squared? X squared over 9. Y squared over 16. What does that look like? An ellipse, right? An ellipse, horizontal or vertical? Which one's bigger? This is our a squared. So is it horizontal or vertical? Vertical, right? Centered at 0, 0. So our major axis is from 0, 0. We're going up 4 and down 4. And then out 3 on our minor axis and back 3. And there's our ellipse. So we got to figure out which way we're going with this guy, right? Okay. So if we plug in 1 or some other number that's nice, let's plug in theta equals 0. When theta is 0, okay, so cosine of 0 is what? What's cosine of 0? 1, right? So 1 equals x over 3, so 3 equals x when theta is 0. And sine of 0 is y over 4. What's the sine of 0? 0 times 4 is still going to be 0, right? So when x is 3 and y is 0 when theta was 0. And then let's plug in pi over 2. What's the cosine of pi over 2? 0, right? So at pi over 2, x is 0. And at pi over 2, the sine of 0 is 1. Take it times 4, you'll get 4. Okay? So when we were at, over here, we were at 3, 0, at 0 degrees. Then at 90 degrees, right? Then we went to 0, 4. So it's telling us that at 0 degrees, we were here. It should likely rotate counterclockwise. Okay, so what I did was I said, okay, let's try theta equals 0 and see what values we get for x and y. And then let's try theta equals pi over 2 and see what values we get for x and y. So when theta was 0, should say 0 here, cosine of 0 is 1, and 1 times 3 is 3. Okay, sine of 0 is 0. 0 times 4 is 0. But now when we're at pi over 2, cosine of pi over 2 is 0. 0 times 3 is 0. But at pi over 2, sine is 1. So 4 times 1 is 4. So basically we're rotating counterclockwise, which is what we were anticipating. I'm sorry. Because at 0 we were at 3 over 0 up, and then at 90 degrees we were at 0 over 4 up. So we're going in a counterclockwise direction, which is what we've defined it to be. All right. Good with that one? Okay. All right. So assignment is going to be 7 through 25 odd on 10-6, page 737.